Erwin Schrödinger. Sunday is my birthday, so today is my great big birthday celebration here at Mobius. I'm well over 100 years old. I know what that said. Thank you very much. On Sunday was my birthday, but we were closed. We were closed yesterday. So today Mobius is open to celebrate my birthday. Now who can tell me a bit, who was here for quantum entanglement maybe, who can tell me a bit about quantum physics? Anybody remember what we talked about an hour or two ago? Yes, sir.
So, like zero,
Photon? Yes. So quantum mechanics is the study of very tiny particles, the tiniest possible particles. I helped found this field, and in 1973 I won a Nobel Prize in Physics for some of the work I did in quantum mechanics. There was an equation I devised called the Schrödinger equation, for obvious reasons, that describes the changes in the state of a quantum system over time. That's very complicated to get lost. The gentleman here mentions that in quantum mechanics, when you observe an object, this is from an activity we did a couple of hours ago. We'll do again at 4 o'clock called dodgeball. But here we're going to talk about something a little bit different. See, quantum mechanics, as I said, is the study of very tiny particles. The tiniest possible particle. What is the smallest thing you can think of? Anybody? An atom. A grain of sand. I'll tell you, an atom is much smaller than a grain of sand. How about you, sir?
over here, I can see it out.
A speck of what? Dust, maybe? A speck of pollen, very small. Excellent. And nucleus is part of an atom. Excellent. Good. Good. Very small thing. Quantum mechanics deals with things smaller than atoms. Things that make up atoms. Particles called quarks, bosons, very strange names like that. So small that you cannot possibly see them with even the most powerful, largest microscope in the world. But we can observe them. We just kind of see them with our eyes. And we know things about them. They're so small. They behave in very strange ways. Very strange indeed. And one of the strangest ways that these tiny particles behave is something called a big word, superposition. Say this with everybody. Superposition. Very good. Now what this means is that one particle can exist in different ways, in different states. Like, for example, water can be either liquid or ice. It can be frozen or it can be quantum particles have different properties that can change and shift. Water can only be liquid or ice at different times. It cannot be both at the same time, right? Anybody think of water can be liquid at the same time? No, cannot happen. Not in the normal side world. But quantum particles are so tiny, so weird, and so strange that they are everything they can possibly be, all at the same time. Let me give you an example. If you were here earlier, we talked about electrons. You remember electrons, very tiny particles with orbit and atoms. They have a property called spin. It's kind of like things spinning in normal size world, but not normal size. They can have two spins, either a spin up, or they can be spinning down. They can spin up, or they can spin down. But because they are tiny quantum particles, at any given moment, they're actually spinning both up and down at the same time. Does that make sense? Not in our normal size world where something has to be either spinning one way or the other, but electrons are always spinning both up and down at the same time. Until we observe them. When we observe them, they fall out of this superposition. Superposition again is where they are both spin up and spin down at the same time. And they choose one that they can make. So when you observe it, you see it as either spin up or spin down. Until then, it is both spin exactly at the same time. So this does not make any sense given what we understand about our normal size world. Do you have a question, sir? So it's split in two and shot in two separate directions. At that point, however, there's two different parts of the fireball, correct? An electron is only one thing, spinning both directions at the same time. It does not make sense, I understand, because we're not used to thinking like this. Because in our normal size world, something cannot spin in two directions at the same time. It can't be two different things at once. But there were some physicists, when I was working, who thought that this was possible. It's like, for example, the moon would be both a crescent moon and a full moon until we looked at it. And that's just simple, right? There's a harness. And I designed a thought experiment. It's an experiment you just think about what it's actually doing to demonstrate why I think this is so simple. Here's the thought experiment. You need a box, and you need a cat. You open the box, and you put the cat in the box. You put three more things inside the box. You put in a radioactive atom. It could be emitting radioactivity. You know radioactivity, right? Dangerous stuff. Two, you put in a Geiger counter, which is just something that measures electric or radioactive activity. So it knows when the atom is giving off radioactivity. You put in a canister of poison gas. And this is what you do. You attach the Geiger counter to the canister of poison gas. So when the atom gives off radioactivity, it is measured by the Geiger counter, which opens the canister of poison gas, which gets released into the box and right up to the cat. A very sad experiment. This is why we never actually do this experiment, we just think about it. But because the atom is a quantum particle, once we close the box, nobody is observing. That means it is in superposition. That means it's giving off radioactivity or not giving off radioactivity at the exact same time. Just like the electron can spin up or spin down, a radioactive atom is both giving it off and not giving it off at the same time until we observe it. And it falls out into one of the other states. But because we have entangled the cat, the Geiger counter, with the canister of poison gas, with our radioactive atoms that is in superposition, everything inside the whole box is in superposition. It goes like, so the atom is in superposition. It is both giving off radioactivity or not giving off radioactivity at the same time. Which means the Geiger counter is both measuring radioactivity but not measuring radioactivity at the same time. The canister of poison gas is both open and closed at the same time. And the cat is both dead but alive at the same time. This does not make any sense. It's ridiculous, yeah? We know a cat cannot be both alive and dead at the same time. So I designed this thought experiment so people can understand why I think this particular fact about mechanics is so strange, so simple. But that's just one way of interpreting quantum mechanics. It's called the Copenhagen interpretation. You don't need to know. There's one way of thinking about it. Here's another. Put the cat in the box. We're not observing it. Because once we open the box, brings the cat out of position, it will be either alive or dead, right? Unless we leave it in there for a very long time, and then it will definitely be dead. The other way of thinking about this is once we close the box, we're no longer observing it. Rather than existing in the superposition of alive and dead at the same time, the world splits into two different universes. In one universe, the cat is alive. In the other, the atom has given off radioactivity. The canister of poison gas is open. The cat is dead. The only way to know which of these universes we are in is to open the box and find out. That is in any world's interpretation of quantum physics. Very complicated. We don't know for sure if these other universes exist because the other universes we cannot possibly observe. But back to Copenhagen interpretation, when I talked about before, superposition, the cat was dead and alive at the same time. It gave me so many headaches that came up with this experiment, the cat in the box, and it became so famous they even called it after me, Schrödinger's cat. It's very difficult to wrap your head around. Because quantum mechanics operate the same way as stuff all the size world does. But you don't quite understand. It's perfectly fine. Even very smart scientists like me understand quantum mechanics. But now we have to open the box. So put the cat in the box. It is time to see if he is alive or dead. Oh! Well, that was unexpected. This is my father's parent.